Now, okay. Now let's start the class. In the last session, we just gone through the DC characteristics of diode, how a diode works in a, when DC input is given to it. Now in this class, we'll learn how it works when we give AC input to it, and also we see that MOS capacitor device. So for the diode, this CMD file is when we are working using diode as a DC input, and this is a CMD file when we are giving AC input that to that diode. So what are the basic difference here? You can see that similarly in that case we have given that P contact and N contact. Here also we have given that N contact and P contacts. In DC characteristics, we are just measuring the IV characteristics of the diode. What are the currents varying when we are giving different voltages to the that diode? In this case, we'll gonna measure the capacitance of at various points in the diode. So whenever we measure capacitance of a diode, we require two terminals because capacitance occurs only between the two terminals. So here we have defined, you can see clearly see that this we have defined N contact as NC and P contact as PC. This is just to define that it we are measuring that capacitance between the two junctions P and. So similarly, like that how we run that DC CMD file, we are gonna run that AC CMD file. Open in a terminal. Now after that running of that CMD file, we can check the various plots and as usual. if anybody is using currently, then any two members can close so that this license can be available here. Now here we can see that what is the advantage of using AC analysis in place of DC analysis. In that DC analysis, we are just only getting the graph between current and voltage. Here in AC analysis, we get both graphs for that current and as well as for capacitance. So this is the advantage. In place of DC CMD file, we can use that AC CMD file in which we can both the plots, that is current IV characteristics plot. This is the file CV diode design dot plot in which we get the IV characteristics, and plus this AC underscore DS plot in which we get the capacitances between various junctions in the diode. So I am just opening this file. So this is our file CV underscore diode underscore AC underscore design. So in this, in x-axis, we take the voltage across in x-axis, and here are various capacitances C, NC, NC with capacitance between N and N junction, capacitance between P and N junction, capacitance between P and P junction. We can select any of the capacitance and just plot it on the y-axis. So we are getting this. Initially, it is constant, but once the voltage is increasing, you can see that it is increasing. So remember that this capacitance value is in femto units. So that's why we are getting 1 upon e to the power minus 14. If your graph is showing capacitance value in microfarad, so it will show a straight line. So be careful, use log x if you are having that capacitance value here in farad, microfarad or farad. Since the capacitance is very small, so you will only get the value in femtos. So for that, just use log x log y command here, so you'll get that this type of graph. You can plot, you can see capacitance in any of the junction like this. So where you can check the capacitance at various points by just looking at this graph and make analysis by yourself. So basic advantage what I have shown here is that when you use DC analysis, you can only see that IV characteristics of any graph or any diode, and when you use this AC.cmd file, you are able to see that IV characteristics, as well as you can able to see this. See, this is, you can see this was the graph you are getting when you are plotting in that DC analysis. So in this AC analysis, you are able to get this graph also. So from next time onwards, you are using, you instead of using that DC CMD file, you can use this AC CMD file. Now, similarly, we can go for the small capacitor. Here is it. This is MOS ac.cmd file. So I just briefly show you what is it. It is having what we know that basically MOS capacitor has one P substrate, then SiO2 या oxide layer, and over it we have a metal. So metal behaves as a gate contact. So we have there are basically two contacts in the MOS capacitor. One is through metal and second is through body. The contact through metal is we have given the name gate contact, and the contact through body we have given the name body contact. These are all physics work. Here we are given that DC voltage, starting voltage minus 1, gate voltage to minus 1, and we are taking our voltage, goal voltage, to 1 volt. That means we are varying our voltage, gate voltage, from minus 1 volt to 0 or 1 volt. So how many range is from 0 to 1, and we have taken 50 intervals. So this basically shows that this file basically show that our MOS capacitor have two contacts. One is gate contact, second is body contact. We have to measure capacitance between the junctions. So we have given that here junction, that is GG, and so contacts to our junction, that is GC and BC, and through junction we can measure the capacitance. So this is basically our CMD file. Again, if we go to SDE, this is our basic device. You can construct it since you have constructed PN junction diode. So this is very easy to construct. It is we have taken that P substrate, doping concentration of e to the power 18 between this P substrate and this metal contact. We have just used SiO2 layer. You can take the thickness of this P substrate to up to 40 to 50 nanometer, and this gate SiO2 oxide layer from 1 to 5 nanometers. Then just use two contacts, metal contacts, one at this body side and one at the gate side. This is the basic construction of our device. So you can construct it by your own. And how to build a mesh, you know that. Just go to the mesh, build mesh. Your mesh will this this meshing successful command will show when you have make the design very completely good. Now, one thing you should remember, this giving that refined placement, it should be its maximum size should be 0.001 in x direction, 0.001 in y direction, and minimum size should be 1 e to the power minus 6 in x direction. Similarly, 1 e to the power minus 6 in y direction. This size you should give. Not do not give size smaller than that. Otherwise, your file will take longer time for meshing. So again, you know how to construct a device. You have already constructed a PN junction diode, so you can construct this device. Now again, I will run this MOS CAC.cmd file, and we see the capacitances as various junctions. So open in a terminal.
Okay, this is the reason why I asked Anshul not to close the visual window. So actually, I can find that there are three jobs which are in queue. So essentially, if any one of you log out of visual, still we are not going to get it. So I'll try to kill some of the visual instances so that one license will be freed. Okay. And Anshul, when you open that visual window, do not close it. All
Okay, sir.
right. Yeah.
Here again, like I have shown in the case of diode, here we get two plotting files. One is AC underscore ds dot plot, which gives our AC analysis, and underscore ds dot plot. This will give us our DC analysis. So this is again advantage here also. So we select this AC, open it. So again, it will show the relation between applied voltage and capacitance. So we are applying gate voltage to x-axis. We can measure capacitance. So here you can show that the capacitance is just decreasing when you are increasing the voltage. So it should, in ideal case, it should go after this. It should go shoot upwards, but it is not going, and it is going flat with the y x-axis just because we are working in a very high frequency in gigahertz frequency. That's why it's not going shooting upwards. It's just following that x graph parallelly. So you can analyze the capacitance as various junction by using this graph. Again, some points you should know that whenever you are designing any this circuit, so mesh, for example, here we have designed MOS C under device. So MOS underscore mesh dot TDR file will be generated. This is compulsory. If this file is not generated, that means your design you have not designed the circuit properly. So whenever you design, just see in your folder that this MOS, whatever you have given the name, I have given the name MOS C underscore. So this name file underscore mesh.tdr should be generated in your folder. Again, when you look at this file, so better change name here. We have given the name MOS C underscore mesh. So if you are giving some other name instead of this, you can give the name here. Again, we have given the gate contact name to gate contact and body contact name body contact. If you are giving some other name, so please do the changes here also. Similarly, here you have to change the name of device, whatever the device you have given. This file is, sir, this file we have not used. This is the file we are just this is the command we have designed for the DC analysis. We have not used this is, so this of no use here. This was there, and when we are using that dc.msd cmd file, it is not used here. Again, here just give gate contact. We have used gate contact, so we have given gate underscore contact equals to gc. You just make name whatever you have given to your contact. Similarly, here body contact, change the name by that contact, whatever name you have given. So for making device, just create a folder, give the name, construct a device, give it any name, copy this mosc.accmd file here in that folder where you have just creating that design, and make the changes according to your design, and run this mos underscore ac.cmd file. Afterwards, that you open that as usual command, and there you can see various plots between various curves. That's okay from my side.
Okay, everyone. So you have already understood like what are the steps. This MOS capacitor underscore AC.cmd file, that command file will be shared on Google Classrooms, which you can download and essentially tweak on that. So as Anshul has rightly figured out, I mean, he has already told you, like the AC coupled analysis will always give you a benefit of giving you both DC and AC simultaneously. Okay. So Anshul, can you actually show the electric like potential profiles and all that using your S visual? It's still open on the left hand side. just beside it. No, the is visual. Correct, that one. So here, the in the standard, like if you are looking for the device characteristics, like for example, the MOS capacitor potential profiles, the diode potential profiles, depletion width, and all those things, you can essentially get it from this particular file. Okay,
Whatever the name of your file is, underscore design.tdr. This file
EDR.
will give the basic characteristics of your device.
Basic characteristics in the sense like those are the 2D profiles. Okay, so the IV and CV, I'm essentially focusing those parameters in these projects, because this IV and CV are something which we will require for the next stage of circuit designs. The potential profiles, which Anshul will show you in a few minutes, those are essential just to investigate more on the device perspective, like exactly how is the variation of the depletion profile, space charge profiles, and all that. But however, that is not going to be very important for us when we are designing the circuits. Okay, for the circuit designs, you need to have the CV and the IV measurements, and Anshul has already shown you how to like convert all these curves into like the CSV files, right? So those export data export part you should learn. And now, just before conclusion of this session, Anshul will show you how to create one X cut, and then yes, Anshul, you can explain. Yes.
This is from here you can make a cut in your device, and these are the various device parameters you can check. What is your doping concentration? So here you can see that it is increasing here. First it is almost negative, then it's whenever you when you are going upwards, it is increasing. Like that, you can check everything from this profile. What is your absolute electric field, acceptor concentration, band to band generation, band gap narrowing. There are many factors you can check. Valence band energy. This is your valence band energy. Similarly, you have conduction band energy. You can compare both the energies with each other. There are various factors. You can go through it and you can check various factors, like what is your absolute electric field, what is your absolute electric field there, and you can analysis whatever we have taught in the class with that whatever the graph we are getting. You can analyze that what is the conditions and what we are getting. Like that, you can analysis various things in your design device.
So here, if you will notice, like Anshul, you can also click on the last button on the right hand side to give the potential profiles. Exactly. Yes, that one. Yes, press OK. So here you will notice that EC and EV, these are these are the pictures which we have already shown in our classroom, right? In today's lecture also, I was drawing the same things. EC and EV, and the EFM, if you can see EFN and EFP, they are essentially coinciding each other, and they are the same even between the oxide as well as the semiconductor regions. Okay, because as I had already told you, a MOS capacitor is a capacitor, and hence it is always under equilibrium. So that means the Fermi energy level is going to be invariant across the entire device, just like the diode case. Okay, so similarly, you will notice that the EFP, the blue dashed line, happens to be invariant. But what is varying are the EC and the EV values. What you will notice, the separation between the red and the green color, that means the EC and EV is much larger, okay, towards the left side, because that is the oxide region. Okay, please understand, all of you should be able to visualize this. What Anshul has done, he has essentially done one X cut. X cut means in the top right hand corner, in the picture, in the screen which you can see in front of you, in the top right corner, you will find he has done an X cut. So that means for a particular value of X, the variation is along the Y. Okay, so that has to be followed for the MOS capacitor anyway. Remember, in the classroom, I was showing that the x-axis was basically the depth of the device. So that is exactly what is represented on the bottom left corner band diagram. Okay, so what we are finding is that it is the y-axis, which is it is the depth which is plotted on the x-axis, and the y-axis happens to be the energy in electron volts. All right. So what we notice is inside the semiconductor, the band gap is only around 1.1 electron volts, as you can see. Inside the oxide region, the red and the green region, the separation is much larger because that is the oxide. Okay. Now the point which I wanted to make here is that, look, there is a slight variation or the slight kind of slope which is observed in the inside the entire region. So none of them are flat, as I was explaining about the flat band voltage. Why is that? Because we have applied, remember, we have applied 1 volt to the gate terminal, and we have put the body terminal to the ground. Okay. So that means you are anyway essentially going to get one electric field from the gate to the ground, gate to the body. Okay. And that is the field which is represented as the slow but gradual slope in the red and the green lines over here. Okay. So I expect all of you to kind of uh, match whatever we are learning in our class, in our lectures, and with the exact simulations what we are doing over here. Okay. Then in the CV curves, okay, we have done the analysis for 1 gigahertz. Okay, so if it is 1 gigahertz, the the charges which are inside the bulk will not have the opportunity or the time to come and invert the channel. As a consequence, you are not seeing any U-shaped curve or the V-shaped curve in the CV characteristics on the top left corner plot. Okay, this is the high frequency or the RF CV measurements, and that is what is represented over here. Further, more details on this, on the theory, will be covered in the lectures as we go along. Okay, so as of now, what we have learned is something which you need to reproduce in your simulation 2 assignment. Okay, where I'll be sharing with you the this AC CMD file. All right, and then you'll have to reproduce or you have to redesign this MOS capacitor and then obtain this capacitance value. Then your task will be to optimize the sizes and the different parameters inside the MOS capacitor. For example, the oxide thickness, okay, the doping in the p-type region. Remember the doping which I have used, unless Anshul has changed it, we have used it as 10 power 18 per centimeter cube. You have used the same only, right, Anshul?
Yes, sir, 18.
Yeah, it is 10 power 18. Okay. So you have to show in your report in simulation 2 assignment, like how does the CV curve change with the doping level? How does CV curve change with the oxide thickness? Okay. These are the various parameter studies which you have to do. In the process, you will become an expert on this AC analysis. And as mentioned by Anshul, that henceforth, you are always going to use this AC coupled analysis, because that will give you the CV and CV as well as IV curves simultaneously. Okay. Any questions, anyone? If not, then we are going to close.
Okay, at last, I'll tell you that this CV underscore whatever you are given the name your file dot underscore AC, this will give you AC analysis. This DS dot plot will give you DC analysis, and this whatever the name of your file is underscore DS dot, this will give you the design parameters whatever we have seen here. So you can check by opening any of the files whatever you want to check, and you can vary anything from here. That's all from me.
Okay, thank you, Anshul. So now it is up to the students to practice this and complete the simulation 1 assignment first, and then simulation 2 assignment will be coming up. Okay. Now, after you have done the IV and CV, then the next thing that we are going to study is something called Centaurus Workbench, where we are going to do this AC analysis, essentially meaning that the both DC and the AC characteristics we will be getting, but we are going to do it as a batch process. Okay. So that means whatever parameterization you are doing it manually, right? You are changing the oxide thickness, you are changing the doping manually. So what we want to do is we will essentially parameterize those, and in one simulation part itself, in one simulation go, we are essentially going to get the entire data set for all the parameters for all the variations. Okay. So that's all for today. Thank you for joining. This recorded video will be again uploaded on the YouTube, which will be shared with you again on Google Classroom for the future. Okay. Is that all, Anshul?
Okay, sir.
Yeah. Any other students? Any questions? AC dot, yeah. So AC dot CMD file, if you will notice, Anshul, can you open that? Yes. Mostly you will find it is essentially the same as the DC one, okay, which was done in previously. The only difference is because of the AC analysis, and especially at high frequencies, there are several interferences coming into the picture. So it is not just the DC device which is into the consideration. So that is the reason why you have to give a specific name for this entire system. That is what he has written as device MOSC. This line was missing when we were dealing with the DC analysis. Okay. Then this electrode plot and everything are remaining exactly the same as the DC CMD file, nothing else. Then you scroll down, Anshul, towards the solve portion. Okay, here you will notice that I have commented out the solve section over here, because that is the solve section which was there in the DC CMD file, which I have commented out because we have to add something more to it, so that, but I have not deleted it, so that in the AC CMD file you will be able to figure out what are the essential differences between the AC and the DC analysis. Okay, scroll down a little bit more. There you will find that because of the AC extract, remember, as I told you in the lectures also, like whenever you are measuring the currents are measured across one node. Okay, whereas whenever you are measuring the capacitance is measured across two nodes. Okay, so it is always CGS, CGD, whereas current is measured as ID. Got it? Current is measured as the current through the drain terminal, whereas you cannot say what is the capacitance at the drain terminal. No, that's a wrong concept. What is the capacitance between the drain with respect to the source? Excuse me. So essentially it's a relative term, capacitance. Okay, and that is the reason why we you can see over here below the dash lines, file AC extract, and here I have mentioned the name of the system. That is the first line, MOSC, which is the device. Okay, then later on in the system part, as system is basically, which is not just the device itself, it will also include the parasitics involved in the system. Okay, so that is one of the reasons why most of the characterizations which are done by the device people, or mostly the characteristics done by the materials people, they actually restrict themselves for the IV measurements, which is not exactly usable from the circuit's perspective, especially at the high frequencies, because they are not making any consideration for the capacitance. Because whenever you are trying to put any device into a practical application, into a smartphone or something, remember you are going to make the device work at a few gigahertz, and that is the reason why you have to consider it as a system. Okay, system means including the load, including the interconnect capacitances, including the metal terminal which you are using. Okay, so that is why we have to do the AC extract term, and then we are defining the system. That means system means what are the different terminals you are going to find out the relative charges and the relative capacitances. Okay, these complications are not there when you are doing the DC analysis. Okay, DC means frequency 0. All right, so here if you'll notice the second line, the first line under the system is MOSC. That is essentially the system name, device name, the first line of this file. Then the gate underscore contact, body underscore contact are the terminal names which we had given in the SDE file. Okay, in the device. And then I have connected to GC, stands for gate contact, BC for the body contact. Why? It is just a short form or abbreviation of the same contact names, because here in the system I have to add the, you can see what is the voltage source preset, V source underscore preset. That means that is the voltage source. The preset voltage source is basically VG, small vg. I am defining it, but under what condition? GC comma 0. I mean, it's not comma, it's under the first bracket. That means we are essentially finding out the voltage VG, which is the voltage across GC with respect to the ground. That is important. Okay, because previously you might ask in the DC analysis and all, we had already put the VG gate contact potentials and all, but those are all the absolute voltages. Here we are speaking about voltage with respect to something. This is a simple MOS capacitor, so I have put a 0. Later on, when after the midsem, when we will be doing the MOSFET simulations, okay, over there we will put GC space GS or SC, that is the gate contact and the source contact. Okay. Now, notice the initial voltage value we had put as a DC as -1 volt, because if we want to even capture the accumulation region, we need to ensure that there is a negative sweep of the VG as well. So that's the reason why I have put -1. Scroll down a little bit more, Anshul. Yes. Then again, the solve section happens to be exactly the same. But what is important is, Anshul, can you select this AC coupled part? Below. On नीचे AC coupled. उसके नीचे. Yes. You can just highlight that. Correct. This is the portion which is the new thing about the AC CMD file. That means all these calculations will be done based on the frequency which is starting from 1, and the end frequency is 1E9. As I said, we are doing it doing the analysis for 1 gigahertz. 1E9 means 10 to the power of 9, that is 1 gigahertz. Okay. So thereafter, what you are noticing is that the AC computation will be done from 0 to 1. This time range is essentially for the entire bunch from -1 to +1 voltage. Because why it is +1 voltage? Notice we have also mentioned just before the highlight of the AC coupled. Goal, the parameter is VG.DC. Voltage is +1 volt now. Okay. So the DC voltage of the gate terminal will be shifted from -1 to +1, provided you are actually applying the frequency of 1 gigahertz. समझ में आ रहा है? So that means what we are trying to find out is the gate capacitance of this MOS capacitor. Okay, when you are operating the MOS capacitor at a frequency of 1 gigahertz with a voltage sweep from -1 to +1 volts. Okay, is that part clear, everyone? So that means अगर आपको ये MOS capacitor as a load use करना है, so if you are trying to use this MOS capacitor and you want to charge from -1 to +1 volt at a frequency of 1 gigahertz, then what is the capacitance seen? Okay, that is what we have actually got. Okay, then the AC compute, this intervals is 50. This is similar to the DC CMD file, where we want to have a minimum of 50 points in our plot. Is that part clear? Okay. Any other? Sir, how the AC source CMD file? Sir, was the band diagram in the third graph obtained by using AC source at the gate? Okay. This AC source, whenever I am speaking about the AC source, remember, we are actually sweeping the voltage as a DC only. Remember VG.DC. Okay. However, the frequency is where you are doing the AC analysis into. That you can see over here, start frequency and end frequency, which is mentioned in the AC coupled analysis. Okay. Yes, of course. Of course, this AC source is there. But again, remember, that is the situation of the band gap when you are doing the variation from -1 to +1 volt at the VG only. After the goal is reached. So that means that is under the condition when VG is +1 volt. Okay. And so what I intend all of you to do is that you at least get started on the AC analysis like this, AC simulations, and then as we go along this course, once you get accustomed to this simulation tool, then we will understand much more about it, and also in the theory we will learn way more details about the MOS capacitor and MOSFET as we go along. Okay, everybody? All right. Is it fine? Then I'll just close this recording.